it's trying to figure out where has somebody not gone with the product, right? So how can we have a much better product today than, say, anybody else who's making turbochargers for the market? And that's the key to getting to a higher performance level. And is there an end to that? It just depends on how much money you want to spend in development.
Welcome to the HPA Tuned In podcast. I'm Andre, your host, and in this episode, we're joined by Gregg Jones, founder and owner of TiAL Sport in the USA. TiAL Sport's one of the OGs of the turbocharger support product market, and by this I'm talking about Wastegates and blowoff valves. They've got a range of other products that they're making now as they've expanded their production, but that's what they were probably known for best in their early days. And they founded this company, or Gregg founded this company, back when there wasn't the range of aftermarket options that we've got today. So we find out about Gregg's background, how and why he started TiAL Sport, and get a sense of the lay of the land of the product segment back when he first founded it. We'll talk about some of the specifics and intricacies of blow-off valves and wastegates, and what we actually need to know when we're choosing and installing one of these products. We'll also discuss his business relationship with past podcast guest Robert Young, forming Xona Rota, a manufacturer of bespoke aftermarket turbochargers. Before we jump into our chat, for those who are new to the Tuned In podcast, High Performance Academy is an online training school. We specialize in teaching people how to build performance engines, how to tune EFI, how to construct wiring harnesses. We also cover topics on fabrication, 3D modeling and CAD, race driver education, and data logging, just to name a few. You can find all of our courses at hpacademy.com/courses. All of these courses are delivered in high-definition video modules that you can watch from anywhere in the world, provided you've got an internet connection. This means you can learn from the comfort of your own place, and you can learn at your own pace. All of our courses also come with a 60-day, no questions asked, money-back guarantee. So if you purchase them for any reason at all, decide it wasn't quite what you expected, no problem, let us know. We'll give you a full refund. And for podcast listeners, you can also use the coupon code podcast75. That will get you $75 off the purchase of your very first HPA course. We'll put the coupon code in the show notes to make it nice and easy for you to find. Lastly, if you like free stuff, then I've got a great deal for you. We are constantly partnering with some of the biggest names in the aftermarket performance industry to give away some great prizes. You can always find our latest prize at hpacademy.com/giveaway. It might be an aftermarket ECU or dash. It could be some engine components or engine building tools, or just about anything in between. They are great prizes, and we will ship them free of charge to your door if you're the winner. There's no tricks here, no purchase required to get your name into the draw. All right, enough with our introduction. Let's get into our interview now. All right, welcome to the podcast, Gregg. Thanks for joining us today. And as always, let's start by finding out a little bit about your background, specifically how you developed an interest in the automotive performance industry.
Well, shortly after getting out of school, decided to essentially have a car interest anyway, right? So I took my machining skills that I'd learned actually even in high school to machine products for performance cars, and started off with a business that were doing custom fabrication, like big turbo systems for Porsche 911 primarily. This was in 1985, 86 range.
Okay.
Yeah, they had just, obviously that was just a recently introduced full electronic control for engines. My business partner at the time was a pretty good computer guy, but I was a good machinist and fabricator. So
let's roll back a bit then. So let's talk about how you build up those skills in machining, because that's obviously fundamental to TiAL Sport these days. So yeah, how did you begin developing an interest in the machining side of things, and then what have you got formal qualifications as a machinist?
So essentially, back in high school, our high school had a really good, strong program in vocational training, I guess we'll call it. So you could do anything from woodworking to metalworking. They even had foundry, grinding. So basically, it was a very well-rounded vocational program at the high school level. Even metallurgy, that metallurgy lab involved in that too. So that was my main interest goal, something I really had a high interest in when I was exposed to that.
But this is also before you sort of started developing a passion in cars, if I'm sort of picking up the timeline, correct?
Yeah, I mean, I always liked cars, but of course I didn't have the resources it wasn't a thing I could act on. I loved cars, but couldn't really act upon it. Didn't really have a path to go. But
They're quite expensive, as it turns out.
especially the fast ones are expensive. So took that skill set. I spent a lot of time, even my spare time, where I could, in the shop, basically learning those skills. So then after, shortly after high school, here where I grew up in Michigan, the economic scenario wasn't great. It was a recession in that time frame, 82. So I decided to move to Florida where there were more jobs available. And that allowed me to exposure to more cars too. Being in Michigan, there were not a lot of, it was domestic car very, very strongly here. And they didn't really involve turbochargers and Wastegates and any of those things.
No, it sort of really, really was the Japanese domestic market models that really brought turbocharging to the forefront around that sort of late 80s, early 90s, as I remember it anyway.
Well, and I only had experience with the German cars. So when I got to Florida, basically there was Alpina was a performance company for BMWs. And then also we had Porsches there. And there was a couple Porsche shops around the area that I lived in Florida when I moved there. Also BMW guys. So first I got into BMW. They had Alpina. They did Alpina turbo kits. That was, was really interesting. So I bought a BMW, got a kit put on it. And, but then I got exposed to Porsche after that. I'm like, okay, I'm going to not do BMW stuff. Now I'm going to do Porsche stuff. So that kind of all to that based on the fact that they had turbo cars and turbos were more widely accepted on Porsches because Porsche had done turbos for a longer period of time. The Japanese cars, on the other hand, I mean, I think I'm thinking of the 80s and nothing's coming to mind, but maybe you might have a better input as to what Japanese cars, but.
Yeah, probably in New Zealand we had no local manufacturing of cars. So we were predominantly Japanese domestic market vehicles. And actually, I'm thinking back, my family bought I think it was a Mitsubishi Cordia turbo.
Okay. Oh, yeah. Mm-hmm.
I'm struggling to remember the exact year of that, but that was my first exposure to turbocharged cars. I can't remember. I was pretty small at the time. And I do remember asking my old man where the button was for the turbocharger. How do you engage the turbocharger? Obviously showing my complete lack of understanding of turbocharging at that point, but also probably pretty understandable given my age. But yeah, that was my first exposure. And then, we had a raft of turbo cars. I mean, I think my second car, is probably pretty spoilt really, was a Mazda BFMR. So the Mazda 323 four-wheel drive turbo, 1.6 litre Mazda BP turbo engine. And, that just opened my eyes to what turbocharging could do. All of a sudden, you've got this small capacity engine that's able to keep up with, at the time, what was a pretty average, let's say small block Chev or something like that with a carburetor stuck on it. That kind of opened my eyes to not only what the performance was off the showroom floor, but more importantly, of course, what you can do with them with just a couple more PSI of boost. Anyway, I digress. We got a little bit off track there. So we'll bring it back. So you've moved to Florida and you're sort of getting this exposure to these markets. Continue with the journey.
Yeah. So what evolved into the Porsche market, or at least, again, kind of coming back to turbochargers and wastegates, it's like doing turbo kits for the 911 Turbo Carreras, which is not turbo. So the turbo was not available in the U.S. direct at that point in time. So the 911 Turbo, which was rest of the world, never made it to the U.S. until 87. And so therefore, all the turbos that were around were gray market cars. What they call here in the U.S. is gray market car. They certified it, they brought it in and certified it, but it was not supported by Porsche in North America. But anyway, the Carrera had come out, and my partner at the time was pretty good with computers and software, had written software for other applications. And so he kind of dove in on the computer side of things for tuning. And we built turbo kits together for the Carrera, for the 84 and on Carrera cars, which was, again, they accepted it very readily. Like, there's a turbo, but I can't get one. So I can take my Carrera or my turbo look Carrera and I can now have a turbo on my car.
Yeah.
And so that's where it started to recognize that the availability of high-end components for that, which we did end up using at that time. We moved over to HKS, like Wastegates. Greddy was available too, but HKS probably was the one that was most available in the US because they actually had a branch in or warehouse distribution in Los Angeles, I think, at that time. So we were able to get, those, and they did work, reasonably well, but they were still cast iron. And I kind of recognized it from my background. Like, I think I could do better, materials and provide something. But again, being in Porsche stuff was, the Porsche wastegate was, resist casting, very high end, but also very, very expensive. Like, so, using the most expensive materials, like, a high nickel chromes alloy for about all those things that were, but again, they had the budget, I guess we'll say in the European, they were willing to spend more money. It was a much more expensive products, but recognize that I could do improvements there. Like the wastegate was kind of thing. I'm like, it's a small enough thing. I could probably tackle that on my own, in terms of like doing the engineering and design. And
so let's look at that HKS wastegate at the time. And, again, as we're talking, probably people are thinking of the current crop of HKS wastegates, but we're absolutely not that. This is back in the late 80s, we're still talking?
Yeah, well, that was still in the 80s, so that nothing was stainless. It was all iron castings.
Yeah. So what's the downsides with cast iron versus, some of these high-spec materials that are being used today? I mean, is this just purely based on the fact that the cast iron will corrode, or are there other performance downsides with a cast iron wastegate?
Corrosion and thermal limits. If you have some thermal things that can happen to iron, normally they would be on like a ductile iron of some kind. Very different variations. I'm not sure exactly what iron they were using for the I didn't analyze it, but a lot of our customers would go to the track, and people would go to what's called PCA events, Porsche Club of America. I had thousands of members, so people would have track days, and we go out and run the cars around the track for road racing wise, and that's where the material limitations of, we'll say not the highest quality materials. Again, not faulting HKS for what they selected. They were economical, and I would say for a non-road racing car, no problem, right? They would work, last fine, no issues there. But we saw from a road racing standpoint that they wouldn't hold up very well, and we have to replace them often.
Sure. Yeah, I guess the thing that's easy to overlook is that on the road, if you value your license, it's very difficult to stay at sustained wide open throttle for a long period of time. But of course, on a road race application, we literally are doing that lap after lap with short breaks from full power as you're obviously in a braking zone or through a corner. So it's a completely different environment for the hot side components to stand up to. So when you are starting to get at or beyond the thermal limits of cast iron, what do we sort of see go wrong with the wastegate? Are we getting distortion of the seeds, or does the thing jam up or melt, or?
Yeah, what we would see is the valve seats, or the valve and the valve seat, would become basically adhered to each other after you ran a session. They would be stuck together from corrosion, from being hot. I say corrosion, you get corrosion, then it comes together hot, and it would sit and it would stick down. So between sessions, where you'd have to unbolt the wastegate and hit it with a hammer to break it off. I mean, again, and I don't want to say like I'm beating up on HKS, but again, they didn't design the component for road racing. So,
sure.
And that was just something. So again, it was back to available materials. And again, we're talking the 80s. So availability of exotic materials and so forth to build a higher end piece wasn't necessarily readily available either. But that was the thing I noticed, like, hey, I think, again, through having exposure to materials and doing materials testing, and even at high school levels, like, I think there's a better material selection potential. And then other design, Turbinetics in the day, which was also wastegate manufacturer, that was very popular right here in the U.S. Turbinetics was probably the largest seller of wastegate back in the 80s. And due to that design, which was a carryover from a Rota design, was a 2-bolt flange wastegate. So it had a lot of problems because it didn't seal well because of the 2-bolt design. So that's kind of, again, looking at that going, I think I can do, even in a 2-bolt design, I can make improvements like that would get better sealing, make some minor changes. Still have the same 2-bolt design, just improve the design.
You're actually just giving me PTSD. I think I'd blocked those memories out of my life. But the number of times linishing those 2-bolt flanges flat because they just leaked. Yeah. I mean, these days, people don't know how lucky they've got it with basically everything we deal with these days is V-band, which just makes our life so much easier. I mean, not without their own set of issues, perhaps, but yes, certainly. And I mean, even from just a physically working on the turbocharger installation, trying to get to a 2 or a 4-bolt flange and all of the bolts, and I'm talking here turbo as well as wastegate. I mean, honestly, what a ball ache.
That was something that, having worked on cars and built cars during that time frame, was like, especially like on the turbo Porsche single turbo, you get to 3 bolts really easy on the exhaust discharge side, right? But that 4th bolt, you had to have a custom wrench to get to it. Like, you were going to get to that thing on the car, you'd have to, disassemble the bumper and a bunch of other stuff, or you had to make a special wrench to get to the 4th bolt. Like, you just drive you nuts, working on cars. Like, isn't this a V-band? It would be easier.
Yeah, yeah. I mean, we've got a drawer full of those bent up wrenches or something welded to something else. We call them special service tools. It sounds a little bit more professional than a bent wrench, but we've all been there.
Yes, right. So again, recognize that as one of the things that I'm like, we should have. So of course, at the time, in that time frame, Garrett Motorsport was starting to do some V-band motorsport housings, right? So this is Formula One, for instance, like that. You started to see some V-band housings mid-'80s on the turbo cars before they switched off from turbos. You start to see some V-bands out there, but nothing in the OEM land or anything in the aftermarket at that point.
Why do you think, I mean, obviously these days, looking back, everything's super clear with the benefit of hindsight. They're simple to work on, as we've just mentioned, but what took so long for the aftermarket to sort of pivot towards V-bands as opposed to bolted flanges?
I think just the natural development, or progression of the market and how the market was changing is that, initial performance market for turbocharger and wastegate kind of carried over from the available turbochargers and wastegates that were on diesels, right? So again, back to, if you're going to, select materials for a diesel, it's not going to work so great on gasoline because it's just a much higher temperature than diesel was, especially for that time frame. To modern diesels, not that way, but back in the day, diesel would run at like 1100, 1200 degree exhaust gas temperature, and gasoline, you're lucky if you can keep it under 1700 F, which would be maybe 900 C, right? It'd be like, that's way too hot for all these components. And so I think it was just because that was what was available. They made wastegates for other applications, and they kind of carried through on performance. Hey, what's available? And Rota Master had made a wastegate for, I'm sure it was some diesel application, and that just got carried over because it was available from something else. And then a few improvements got made.
So it's sort of one of those, if it isn't broken, don't fix it situations. But unfortunately, to a degree, it was actually broken for these road race applications.
It was all broken. Yeah. I mean, I say all broken, but yeah, it was not the best idea. I mean, like you said, you dealt with the 2-volt flange and they would never stay flat. And again, the temperature differential. So diesel's not getting that hot. You're getting distortions and material's not strong. Iron loses a tremendous amount of strength at something that gets to 15 or 1600. So you're warping parts. You got all kinds of, again, back to, it was never really engineered for the application. It was just a carryover, and it takes time to change a market.
Yeah. All right. Well, we've identified a clear and present issue. So you've already talked about you're looking at solutions to this. At the time, with the materials available, what did you sort of gravitate towards? What did you think was going to give a better solution than cast iron that was the norm?
Really, I mean, we started with a very, higher temperature stainless steel material for the body, and we used a nickel-based material for the valves, alloy. We evolved. We get to the point where I'm no longer building cars and doing the car fabrication. I'm like, I want to make wastegates, and that was I started the company in '93 and said, here's my focus. I had other products to make from machining that I'd already made from Porsche stuff. So I kind of carried that product on while I was developing the wastegate. And then I selected the Porsche fitment because that was the one I was most familiar with. So it was interchangeable with the 911 Turbo because that's the market I came from, and made improvements there from the standpoint that the Porsche wastegate had an enormous wastegate top on. Like the diaphragm was just gigantic compared to the rest of the body, right? I don't know if you've ever seen one off of the early cars. They're huge.
Yeah, I've seen one. Yeah.
I understand why they did that is that provided a lot of mechanical advantage to keep the boost very stable in terms of when you start to reduce the ratio of the diaphragm area to the valve area, that's where back pressure from the turbo, as it changes and you rev up the engine, pushes the valve open. So a lot of times when you see boost fall off, that boost fall off was because the back pressure was climbing so fast, it would just push the valve open and it would fall off and boost. And so the Porsche one had such a huge, it was like 5 or 6 to 1 ratio. It would just fight that easily because it had 6 times the area of the valve. And it could just push it there. Like it would just push it there anyway.
That's sort of interesting. Just while you're on that note, it might be worth diving into that in a little bit more detail. So I get that concept of the diameter of the surface area of that diaphragm versus the valve. However, I mean, if we look at the modern crop of performance wastegates from the likes of yourself or competing brands like TurboSmart, they're absolutely not that anymore. The diaphragm diameter is quite small relative to the valve. So what have been the changes that have sort of overcome those issues with turbine back pressure?
Well, okay, so primarily, obviously, I think a lot of times people don't understand the wastegate doesn't really control anything that has to do with back pressure. So it's 100% turbo related, right? So it's the combination of what components did you build turbo with that creates the back pressure to the engine? And Wastegate has nothing to do with that at all.
No, sorry, I guess I was mentioning, more along the lines of back pressure exists.
Yeah, so evolving of turbo technology, right? So efficiency of turbine efficiency, compressor efficiency, and then also, which is even probably every bit as important, maybe more important, is sizing the proper turbine to compressor wheel size. So often early on, a lot of the turbos were built with just bigger and bigger compressor wheels, right, for performance. It doesn't mean it didn't make more power than the one they took off. But what happened is that it's basically causing the turbine to run in a less efficient area. It slows down the turbine. It falls off the efficiency curve for the turbine or on the EC, and then it just back pressure is the only way to drive it.
So essentially what you're saying is those older turbos in that performance market, the back pressure you were seeing back then significantly higher than the modern crop of performance turbos for the same airflow.
Yeah, there's more availability too, right? So component availability, sizes of turbine wheels available. So as you got more selection available to build something with, you could build a smarter build even from existing components if you knew what to put together, right, from a sizing standpoint. And then better designs come along, like you said, computer design, you can better blade foils. It can be designed in CAD because now you can optimize them through engineering software. Those steps in efficiency, and then, but I think often overlooked is the compressor. How much power does the turbine wheel need to make to run the compressor you've put on there? And that's, I think, we're generally speaking that there's the mismatch traditionally. That is, yeah.
All right. Let's talk a little bit about the design process. Yeah, I'm going to make the bold assumption that back when you were learning about machining, this would have been on manual machines, not CNC. So at the point you're sort of looking at designing a better mousetrap with these wastegates, are you now transitioned to CAD and CNC machining, and how did that transition sort of work for you?
So there was a short intro between doing the turbo kits and so forth, which was done on, most of that stuff we all did. It was all manually. I had a Bridgeport and a lathe to do work with, and all those parts were made on manual machines. When it came to the wastegate, it was, really needed to. So I spent a time with another manufacturer that exhaust systems in the Porsche market prior to getting to starting my business. And I had an opportunity to basically learn how to do CNC machining. They had a CAM system. So I learned how to set up, run machines, program, learn tooling to get a start in understanding how to do, modern manufacturing. And so that was in between like 1990 and 92.
Okay, so you sort of hit the ground running 93 with TiAL Sport. Does, not specifically related to this, but does having a conventional manual machining background and understanding of how a lathe and a mill works, does that benefit you when you transition to CNC, or could you come straight into CNC with no prior sort of manual machining knowledge and still get the results?
I mean, having machining knowledge, how to, depth of cut and tooling, a lot of that just carried over. It's just the machine that was using the tool, right? So ultimately, understanding how to do machining even on a manual level, part of that carries over. And you have to remember that the CNC machines of the early 90s are nothing like today's. They were way more basic. You didn't have much memory. Doing 3D surfacing was like, not a normal thing to do, like 3D surface models and create, very intricate molds and so forth. So you would either have to design in very simple shapes so they were easier to program, or a lot of money to invest to go to a machine that would be able to do like a 3D surface. In that time frame, everything was done with like what we'll call a tracer mill. So it's a manual mill with a tracing device on it. So if you had a pattern, you could make a pattern and you could trace it. 3D machining was almost like non-existent from a CAM standpoint in the early 90s. So it was,
I guess it's fair to assume that just like every technology, CNC has come a long way since that period in time. Okay, so the actual design of the wastegate before we even get to machining, what software were you using for doing that?
I used Mastercam because it had both ability. You could draw in it, you design in it, and then you could also machine it. So it was just a single package versus having, say, two different things, like draw on AutoCAD and then try to move it to some other machining. Mastercam here in the US anyway was, the very early, I want to say, available to we'll say small, medium-sized businesses, the more economical. There were certainly high-end systems that were, somebody like say maybe auto manufacturer or tier one supplier would have, but
out of reach for a small business.
Yeah, but not geared towards any kind of small to medium-sized business. So Mastercam was coming on just at that time in terms of like it was really starting to grow in the medium to small business size because it was affordable enough for somebody to buy that. And so I learned on that at the one manufacturer, and then I just bought a seat myself, when I decided to go forward with TiAL. I said, well, I already know how to draw in it. I can program in it, so I can do everything I need in one package. Yeah.
Yeah. How's that transition now? Are you still with Mastercam? Obviously, these days there's a lot of software packages available. Yeah, what's your choice?
There's a lot of packages. We're still primarily on, we'll say more stuff for really a sophisticated machining paths like airfoils and things like that, like, compressor wheel, blade machining. Even today's Mastercam packages is a pretty decent package for blade machining because, as time went on, they kept adding more and more features to Mastercam. So even today, you can do a compressor wheel in Mastercam. We don't. We early on we recognized that if we were going to do compressor wheel machining, that we needed a more sophisticated software to do that well. I programmed the first few compressor wheels in Mastercam, but it was extremely difficult to do and accomplish. So it was like I need to find another software that could do a better job at this. And so as we evolved into getting into more turbo stuff, in early 2000s, the progression away from Mastercam, our general machining. So if I'm machining a wastegate body, I program it Mastercam because I already had the seats. I'd built up multiple seats for my engineers over the years. So, and it can handle those tasks, right? But try to do a very intricate compressor wheel, 3D surface model, point milling.
Not the best product for that.
Yeah, not the best product for that at the time. And so there was a company, it was German software at the time. It was called Open Mind Hypermill, which is very high level. They had a blade machining package, very expensive software, but it was worth the money to spend. I mean, we're talking back in early 2000s, a $90,000 package for software. So it's expensive.
Yeah, that's a pretty big hit.
Right. So you gotta. Well, we didn't pay with that one with a check. We definitely borrowed the money for that one, I think. But we recognized that it had a benefit, right? So its benefit was going to allow you to do very intricate machining on blades that you just couldn't do with any other software, really. Yeah.
Sure. Okay. Well, let's roll back to these wastegates. So at the time you're sort of developing your first one, are you using anything like CFD to kind of optimize the airflow through the gate, or is this kind of all that looks about right? I can see what the HKS gate did, so let's just kind of copy that with better materials.
Well, being that we did a replacement Porsche one, I made some refinements to the Porsche design on that particular one. Made it a little bit different packaging, made it a little smaller packaging, reduced the wastegate actuator size because it was just already recognized that if you put an electronic boost controller at the time, which would be nothing more than a solenoid valve and a HKS or a Gregg boost controller on it, you couldn't control the Porsche one very well because it had so much volume of air in the canister that the solenoid valve can't move the air fast enough in and out, and you couldn't get stable boost control. So we had to reduce the size of that to make it work. Otherwise, the thing was like, it would swing radically. Like no matter what you tried, it would be like 0.2 of a bar plus or minus, constantly trying to correct, but it could never correct because it just, the latency of pneumatics and that volume of air just couldn't do it.
Yeah, I wouldn't have even thought of that, but it makes perfect sense. Obviously, the internal ports through a Mach 3-port solenoid are relatively small. You're not going to get rid of a huge volume of air quickly.
So that was, and then also looking again, being back in with Porsche stuff, that the 956s and the 962s at the time, we were racing cars, got opportunities to be up close to those cars. And they were running Bosch engine management on those, and look at the wastegates. Well, they were running that wastegate top. It was a much smaller piece already. Even that was in the mid-'80s. So I was like, that was another clue. Like, yeah, when I get to this wastegate thing, it's make it smaller because electronic control and its limitations, we'll say the Mach valve or whatever, was going to be a problem. So like we need to make it smaller so electronic boost control works better. So that was an observation I made back in the 80s. And when I got to the 90s, that's what I did. So I made that revision, made a smaller package for that, and then we introduced that product at SEMA in 95.
Okay. I'm interested, on face value, the wastegate does seem to the uninitiated to be a pretty simple product. Basically, you've got a spring, a diaphragm, a valve, and a housing for everything. But for anyone who's actually ever disassembled a modern performance wastegate, there's a bit more going on. What are the challenges other than material strength, which we've already covered, in terms of providing or producing a quality wastegate that's going to give stable, accurate boost control, and just as importantly, do that at elevated temperatures over long periods of time?
Several things. Obviously, for durability, is the interface between the valve and the guide system, right? So it's a dry system because obviously the temperature, there's really no good lubricants that actually operate well when you heat them up to 14 or 1500 degrees. So material selection, for one, is super important still. But the coating that the mating coating that one of those is going to have to be coated with some tribology coating that works at high temperatures and no lubrication. And so the development of durability is where probably the single most expensive thing in the development of a wastegate to make it last for a 24-hour race, which we can talk about more coming up. But, to how do you make something live for 24 hours, where the valve is cycling all the time and not wear out?
Yep. The flip side of that as well is, difficult without the benefit of an image to show this, but you're feeding boost pressure into the underside of the diaphragm, so basically the low side of the top of the wastegate, and then you've got the clearance essentially between the valve and the valve guide, which is going to essentially become a minor boost leak. So how important is trying to minimize that clearance or seal it completely so you don't have boost essentially escaping down that stem?
It's arguably not that. It's a controlled leak, I guess. A better way to call it is a controlled leak under, normal operating conditions and not excessive wear. The other thing too, a lot of people is that a lot of times these are not just vented to atmosphere. Like if you're dumping back into the exhaust system, you have back pressure. So it's kind of counteracting that. There's a little bit of back pressure in the downpipe behind it if you're going to, say, put it back into your main exhaust, which a lot of systems do. So it's noisy if you don't, right? It's very loud if you just dump the wastegate out. So it minimizes the leak from back pressure also, but it's really a controlled leak that it doesn't affect boost control once you've set it up. So it's a controlled leak. Yeah.
So something we essentially don't need to really worry about, provided, of course, we don't have excessive wear in that guide.
No. Excessive, right? Excessive wear or excessive clearance. Too tight a clearance, the thermal expansion of the valve will lock up in the guide. So too tight is bad, obviously, and too loose is just you're going to leak a lot, but still manageable. But if you get minimum wear, and then you're good. It's a predictable thing, and it repeats.
Yeah. Okay. All right. So, if we sort of fast forward a little bit from that initial wastegate, what did the development cycle look like? Where did you sort of find potential for new products? Obviously, if you're dealing solely with the Porsche market, probably quite a big market in and of itself, but obviously there's a wider range of performance vehicles that need wastegates.
Yes, again, back in the 90s, not a lot of stuff available, not a lot of turbo cars available. What would evolve would be what was the most popular fitment, right? And though my wastegate was not the lowest cost option in the market, clearly Turbinex was certainly selling a lot of product because of its cost. So a lot of kit manufacturers would select Turbinex. They get a turbo, they get a wastegate from them, and we're like, okay, so we have to develop that, fitment to gain market share and awareness of the market. Because the Porsche market clearly is a very small market, but when you're a company of one, it seems pretty big.
It's all relative.
But if you want to grow it bigger, then you reach into other markets. And again, that was where the growth is. Obviously, in the 90s is where, at least in North America, was starting to really grow a lot because the Honda market, I think, was, the import and Honda kit manufacturers for turbosets was like everyone wanted one, I guess, or at least every 18-year-old wanted one in LA, I guess. And that really drove, the market kind of forward. And so it was clear that we needed to make something. So that's how we kind of expanded our market. The blowoff valve also was started. I added that blowoff valve in the late 90s because HCAS and Getty also had blowoff valves. And
it seems like a natural progression if you're going to be making supporting products for turbochargers.
Yes. Yeah, I think so. It made sense, and like you had mentioned before, was that what is its main benefits, right? And it's compressor surge. Clearly, when you close the throttle, you don't want to hammer your compressor blades.
Well, let's rewind a step. So, Greg and I were talking just briefly before we started recording, and one, I think, let's call it urban tuning myth. I think that's probably how I'd refer to it. So when I was growing up and learning about cars, well before I ever started a performance workshop, and these blow-off valve things came about, and they sounded pretty cool at the time. Now I do everything in my power to make my cars silent, but maybe that's just showing my age. But it's sort of pretty widely understood that the purpose of the blow-off valve was to aid response on a gear shift. So when we close the throttle, the turbo's spooled up, it's spinning at 100,000 RPM or whatever it might be, and it's producing all of this airflow that suddenly has nowhere to go. So I think that the urban myth that I always heard is that the turbo will stall, or even I've heard people say it'll spin backwards, which, I mean, knowing what I know now and also watching turbo speed, is absolute garbage.
I don't think it never spun backwards, but it does.
No.
I've seen data. I mean, we were fortunate enough to work with OEM race teams, and when they were allowed to have the valve on the cars, there was clearly an advantage from a turbo response. I mean, most people didn't have data logging. If you think about it, how many ECUs in the aftermarket and data logging, when did that start? And I don't think most people today still only use a turbo speed sensor. So,
I mean, those turbo speed sensors have only really been easily accessible to the average enthusiast for, I want to say, maybe 5 to 10 years. Prior to that, it was, the turbos provided no provision to fit one. So if you wanted to fit one, it was an absolute major machining exercise to try and get that thing pointed at the compressor wheel. Now, we buy a turbocharger, and a lot of them have a nice little boss that's blanked off, and if you want to put the turbo speed sensor on, take the compressor cover off, drill a hole, you're good to go. And we've obviously also got data loggers that easily can read this information. I mean, simpler times. So there was a lot we didn't know, I think, back in that sort of late 80s through to the 90s, even to the noughties probably, I'm guessing.
So a couple of rules organizations during that time frame we're talking about, where, again, you couldn't get access to this, but OEMs obviously had turbo speed sensors and so forth on their race cars, and we'd see data logs, and they considered it an anti-lag device. Some rules outlawed them. Like, you couldn't have them because they're like, well, no, it helps the turbo speed, and it's if not everyone has it, then we're just gonna no one has it, right? And this is back in the 90s. So, and that's why you heard a lot of chirp, chirp, chirp on all the performance road racing cars, because if they weren't readily available, right? So bypass valves would have to be custom made to go onto the cars to even do this, but it was not, it was regulated out. Because there was an advantage to it. But there's multiple advantages besides the turbo speed. If you're looking at shaft speed and shifting the car like in a road racing event, you're going to see a difference. You're going to have more shaft speed retained on the shift than if you didn't have it. Because your compressor is working against a huge pressure spike as it can't. So it does slow it down very dramatically. It's very brief, but it does it very quickly. But you can definitely, in today's modern data logging, you would definitely see it. But you also can damage the older turbos were not ball bearing turbochargers, where it had really high thrust capacities. You can also bend compressor blades, right? So you can bend, if you have a severe surge event, you can bend the blades backwards on the compressor. So
that's always sort of been my take on probably what I would have seen was the key benefit of a blow-off valve, was to prevent that surge on a gear shift, which puts huge thrust loading into the turbocharger core. And like you've just mentioned there, back in the earlier days of turbo technology, we were journal bearing with maybe a production turbocharger with 180 degree thrust bearing in there, which is not great at the best of times. And now you're putting this massive shock loading or thrust loading into that on the gear shift. Obviously, that's not going to last that well. But these days, predominantly, well, yes, obviously, journal bearings are still very, very much a product. If we're dealing with a ball bearing turbocharger, which has such a massively higher sort of strength and thrust, is that side of the benefit of a blow-off valve now kind of irrelevant on those turbochargers? Or are we still considering that maybe bending a blade is problematic in severe surge?
I was curious, maybe make it a little bit broader explanation of why it would still. So if you're doing, a very refined compressor wheel, that you would do, blade thickness is important. So you want to minimize blade thickness as much as you can, for several reasons, aerodynamic reasons, structural reasons. And so therefore you can make thinner and thinner blades. And then if you have a huge surge event, you're going to bend a blade that you wouldn't normally see bending if you have a blow-off valve on. So from that perspective, you have to design the turbo wheel to still handle the surge event and not bend a blade. That would be the main thing. So like you can't get maximum performance from the compressor wheel if you're going to subject it to a 5-to-1 pressure blast every time you shift the gear. So you're
So you're sort of walking a bit of a tightrope here, designing a blade that's maybe not aerodynamically optimized because you need to build in that additional strength to support a surge event.
correct. Yeah. So you can just over-engineer the compressor wheel to have very high durability, but you're leaving performance on the plate. Like, in other words, like you're not getting the highest flow rate, you're not getting the highest efficiency, you're not getting so again, it's a balance. Like, what are you going to use it for, and under what conditions can you do that? You have to make those decisions. And turbocharger design is going to have something that's going to be generally robust, right? Like, we don't know how the customer is going to use the product, so therefore you want to make it as robust as possible, because he may not put a blow-off valve on there, and then you get stuff back that's bent, right? And then he blames you,
Yeah.
for the problem, and they're like, well, you could have run a blow-off valve, right? It's one of those things that not everybody can do it, right? So not everybody wants to do it. So you have to balance, again, back durability versus performance. It's like an F1 engine. Well, how many races does it last? Well, they last more now, but before it would be, you had a qualifying engine and only did qualifying, and then you had a race engine that ran one race, right? So, you have to push that kind of a decision making, I guess.
Yeah, I mean, take us back where budget caps weren't a thing and they could really just send it as hard as the engineering allowed. I think that was maybe simpler times, but obviously, not viable in today's global economy, unfortunately. All right, so in terms of blow-off valves, you kind of covered the fundamentals there. One of the questions that always crops up is, where should I mount my blow-off valve? So obviously the two options there are mount it close to the turbocharger pre-intercooler. Benefit, as I see that, or as is argued on the internet, is we are then not putting so much heat loading into the intercooler because we're venting hot compressed air before it goes through the intercooler, so we're not heat soaking the intercooler so badly. The other sort of argument is that we mount the blow-off valve as close to the throttle body as possible, because obviously that's when the throttle body closes is where the pressure initially starts to back up, so we're venting it before it can make its way back to the turbocharger, perhaps. Downside, of course, is the opposite of what I just mentioned, and that now all of that air that we're going to vent to atmosphere or vent back pre-turbocharger has now been cooled by the intercooler, kind of for no real reason. I'm really keen to hear your take on this.
Yeah, I think there's a couple ways you can look at it, depending on, again, kind of maybe use, like how it's going to be used. So you have a temperature limit. Most blow-off valves today have usually some kind of Viton or similar O-ring to seal, so you get a really good seal at the valve seat area. And that has a temperature limit. So if you're generally staying, let's say, under, that temperature threshold where you can kind of degrade the Viton from temperature, then you could go ahead and run it pre-intercooler. So I won't disagree that you're adding additional load, that if you're, it would be an advantage, let's say in road racing, for instance, like you want your intercooler not to do any additional cooling it doesn't have to do. So therefore it would be an advantage. As far as its placement due to throttle versus the other thing, it'd be like, well, you're not pressurizing all your intake tubes and some other stuff with that shock load coming back all the way to the other side. And I've seen things, but I would say that's a minor consideration. Really, we generally recommend customers put it, as a general rule, after the intercooler, because generally they don't have that restriction of the intercooler requiring, like, so what if you put an extra pound or two through it? Like, what are you doing? And you have a chance of ruining the blow-off valve seal by running non-cooled air through it. So that's really, again, we would advise people based on that. So I generally just say a safe installation would be after the intercooler, before the throttle, because you don't have to worry that you'll overtemp it.
I hadn't considered the overtemp. That is an interesting one. I'll just give my take on it from a non blow-off valve manufacturer. So I don't know how much sort of value you're going to put on this, but I mean, I kind of look at the OE market because that's kind of the upper echelon. They've got no real budget constraints, so they can do whatever works. And in that market, you see both options. So to me, I kind of feel like that says enough about the importance of location. I mean, to the point that these days, a lot of factory turbochargers will have the recirculation valve actually physically mounted into the compressor cover to aid packaging. The other issue that I see is a lot of performance car builds. We have this problem where you've got very tight constraints on space. Like physically, the engine bay has a lot going on, and sometimes I basically will choose the blow-off valve location based on packaging. Like, where can I physically fit this that makes sense? Is that viable, what I've just said?
I generally think so. In other words, if you have a packaging restriction and you say, I really don't have a way to do this, post intercooler, again, you have to consideration what's your outlet temperature for your compressor. So you're going to need to be up around, 2 bar boost or higher in most applications. So you exceed temperatures exceeding the capability of the O-ring.
Yep. I guess to sort of add to my point about OEs, they're not driving the turbocharger in a factory application hard enough to exceed the temperature. So, I suppose let's take that into account as well, just to fully round out what I said before.
Yeah. So, that's why an OE could easily just say, I'm going to put it in the compressor housing because the compressor housing is not going to get hot enough to degrade the material. So there you go. It has been considered, I'm sure, along the way. And I don't know of any OEM turbo engine yet today, none I can think of, that would run more than two bar boost factory, right? So therefore, yes, there's materials that can handle it, and sure, why not package it in the compressor housing because it's right there, right? And they do that. And again, same thing would be true for the blow-off valve. You could mount it pre-intercooler, and same thing would be true.
Yeah, okay. I just want to take a moment out of our interview with Gregg here and talk about a course that I know those listening to this interview are going to enjoy. Really, when it comes to all of the components that TiAL Sport produce, these all really need to come together with being tuned correctly. And that's where our EFI Tuning Fundamentals course comes in. Normally valued at $99, you can use the coupon code TiAL50, that's TiAL50, to get $50 off, bringing it to just $49. This course covers the fundamentals of EFI tuning, including the engine operating principles of a 4-stroke gasoline engine. It's really important to understand these principles so we can actually understand how the engine works and how it responds to our tuning changes. We'll talk about the air-fuel ratio, what that means, and how it affects the operation of our engine. We'll also talk about the fundamentals of electronics, because when it comes to tuning, we do need to understand a little bit about how the EFI system works. This moves into our EFI components, and we'll learn all about the different components that make up an EFI system. Next, we'll move into the engine management system tables, essentially the tuning tables available in our ECU, what they mean, what they do, and how we go about optimizing them. We'll learn about the fuel injectors and find out that these are actually much more complicated than most people think, and having a thorough understanding of the operating principles of the injectors is going to make your tuning much, much easier. We'll then move into how the ECU works, including the speed density principle, calculating mass airflow, calculating mass fuel flow, and then we'll talk about cycle time, injector pulse width, and then how to correct your air-fuel ratio. We then move into the actual tuning process itself. We'll talk about tuning the ignition and tuning the fuel delivery, and also understanding one of the most important concepts in EFI tuning, and that is knock or detonation, one of the most common killers of any performance engine. Then move into what you'll actually need to start tuning and the tools of the trade when it comes to EFI tuning. As usual, once you've completed this course, you will receive a PDF certificate of completion, which is the perfect addition to your CV. So remember, that course, use the coupon code TiAL50, that's just $49. You are still protected with our 60-day no questions asked money back guarantee, so there is zero risk giving this course a try. You can also break that payment down into as many as 8 individual weekly payments to make it as affordable as we can. You'll find a link to this course as well as that coupon code in the show notes. Now let's get back to our interview with Gregg. All right, some other sort of intricacies with aftermarket blow-off valves. Most of them, I think people want to hear the noise of the blow-off valve. And I guess as I mentioned before, I don't really anymore. But yeah, this is a personal preference thing. It sort of goes along with the Wastegates. When I first started my performance shop, that was all the rage here in New Zealand. Everyone wanted a vent to atmosphere Wastegate. And at the time, that seemed pretty cool. And again, as I got older, I sort of like, I don't really want to actually hear that. So started putting them back into the exhaust. Kind of our hand got forced here in New Zealand anyway, because it was made illegal to have them venting to atmosphere. So yeah, long story short, that kind of went out the window except for certain drag race applications. But in terms of the blow-off valve, the other issue that we have with these is how the ECU operates. And what I'm getting at here is if we are running with a mass airflow sensor, vent to atmosphere blow-off valves can be problematic. Can you give us sort of a rundown on how that sort of pans out?
Well, yeah. I mean, any ECU, they'd be running a mass airflow sensor, traditional, either hot wire or something similar to that. If you're you're moving that mass airflow sensor and putting it in front of the turbocharger, you need to put that air back after the mass sensor, right? So that it is recirculating. So you really need to, you should recirculate it. It's really difficult to get it to run well, or you're just going to keep the blowoff valve closed a lot more. It doesn't work functionally as well because you're putting a really heavy spring in it to keep it closed under these certain conditions where you're going to basically vent metered air, right? And then it overfuels the engine and kills it. So recirculating is obviously the right solution for a mass airflow sensor of any kind. That would be the best solution. Then it can have normal operation with the spring and so forth, and you don't have to worry about the car stalling. So
yeah, just to add a little bit more detail for those who kind of maybe aren't picking up what we're putting down here, the problem with the mass airflow sensor, if it's fitted pre-turbocharger, which in a lot of cases it will be factory, is, as Greg said, it's metered the air going into the turbocharger, and that's what the ECU is then basing its fuel and ignition scheduling off. But the problem, of course, when we lift off the throttle and the blowoff valve opens, that metered air is now no longer making it into the engine. It's now getting vented to atmosphere. So the ECU is now essentially overfueling, and this can cause rough running, stalling, all sorts of nasty stuff. So that's why we prefer, or preferably the recirc is the way to go. There's some other issues that, as you were just talking about, that I actually had forgotten about, but a lot of cars are also very, very sensitive to surge. So if you've got an airflow meter that's mounted quite close to the turbocharger, if you don't have a blowoff valve, or you've got a blowoff valve that's maybe undersized for the application or not opening quick enough, you're still going to get some surge come back through the turbocharger, and that can actually go back out through the airflow meter. And then we have another issue. The airflow meter is essentially measuring the same air multiple times. And again, we get this overfueling and stalling. So there's a lot of issues around the mass airflow sensor. Fortunately, in the aftermarket, we seldom use them, so less of an issue. But what options are there for recirc valves versus vent to atmosphere that TiAL offer?
We have a couple different ones. We have a QR was the first one, which kind of converted our initial Q blowoff valve, which was vent to atmosphere, and allowed it to do recirculating. We later developed another valve that was, I would say you can still vent it to atmosphere, but was designed to be able to have a high flexibility for application to be installed for recirculation, and it's a QRJ. It also changed the function of the direction of air. So part of the design of the QRJ is that the pressure doesn't influence the valve position, which a lot of people don't necessarily fully understand. But the air approaches from the side of the unit and then exits the bottom. So there's no real pressure influence from boost pressure building on top of the throttle plate. When you're throttling the car, that extra pressure wants to push the valve open. So you can get these conditions where it doesn't drive very nice because it moves the valve up, then it drops off the turbo speed. So it goes back and forth, and it doesn't drive nicely. So having it not influence that, you get much smoother part throttling conditions for what we call our QRJ blowoff valve because of how it operates.
Yep. Okay. Interesting. One of the points you've made there is about the spring, and I kind of think just back to my own experience with fitting hundreds, if not thousands of blowoff valves from a variety of manufacturers over the years, is that in 99.9% of situations, I never gave a second thought to the spring and the blowoff valve. You kind of take it out of the box, you fit it to the car, and you're good to go. There have, however, been a handful of cars where the blowoff valve would actually get sucked open by manifold vacuum at idle. And this is quite rare, but it did happen, which was problematic, again, particularly if you're dealing with a mass airflow sensitive car. So can you tell us about the relevance of the spring, what we need to know? Is this sort of a fit and forget, or do we need to tune, I guess, the blowoff valve for the application?
Well, being that there's, traditional blowoff valve doesn't really have any direct connection to the ECU, where some of the newer OEMs actually have electronically actuated ones. In this case, you're going to try to select a spring, again, with mass airflow systems that would keep that valve closed at idle. So you would measure vacuum at idle and make sure the spring pressure was enough to maintain the valve closed near idle conditions, right? That would be the way you would have to size it for anything that was going to vent to atmosphere and not recirculate for any mass airflow sensor car. If you have speed density, it doesn't matter.
Yeah, sure.
But yeah, so that's how we would do it. So measure. We would always ask people. People ask like how to size it, like what's your vacuum on your engine, and then that's it, idle. And then you would, that would tell you to do it. You would just make sure it stays close so it doesn't cause you problems if you're going to vent to atmosphere.
Yep. I think just something that people should be aware of, because most people just do what I mentioned and take the blow-off valve and fit it and never think too much more about it. So there are a few considerations there. The other choice that people need to make, of course, is blow-off valve sizing. Have you got any guides on what people need to consider in choosing an appropriate size blow-off valve?
It's less sensitive than let's say Wastegate would be, like understanding the exact flow rate. You can have a little bit bigger size blow-off valve and not necessarily really affect its operation much. Comparatively speaking, because you're just releasing pressure generally. Once the pressure spike is going to be gone, it's closed again under most, so you don't really see that. So the size is less important. Otherwise, you want to make sure it's enough so that you're not getting compressor surge. So most of the valves are quite large for at least aftermarket ones anyway. So even our smallest valve is sized such that it would work for engines, that are much higher output. And we have flow ratings. We did flow testing and so forth. So you can look at how much your turbocharger is flowing, and then go to the chart and go, is this going to be enough flow versus how much boost pressure? So we actually have a flow chart that you could select to go make sure it has enough flow. So you can bypass all the air.
But essentially what you're saying is, if in doubt, bigger is always going to be better than too small.
I would say there's not a lot of detriment to, let's say, a valve is, we did 50 millimeter valve, which is a tremendous amount of flow. Like it can work on a 1500 horsepower engine, right? So it's that guys are running around with 200-300 horsepower, and it doesn't change its function in terms of interfering how it works, or for the engine itself. So it's less sensitive. I would say significantly less sensitive to size. And go bigger. If you're in doubt on that one.
Bigger's better. Not always with turbochargers, but yeah.
Well, not even for wastegates too, because that's your misconception there that a bigger valve is a better thing to do, and that's not always true.
Yeah. All right, well, that's a nice segue into a bit of a deeper dive on wastegates. I think we've probably covered the blow-off valve. All right, so when it comes to wastegates, obviously sizing of the wastegate is probably one of the most critical aspects. Choosing an appropriately sized wastegate to control boost, and this is quite complex because there's a lot of moving parts in it. If you end up with a wastegate that's too small, you're going to end up with your boost sort of spiraling out of control as RPM rises, which is obviously no good to anyone. What does the enthusiast need to understand about choosing a wastegate that's going to suit their application correctly?
I think there's definitely a general rule of thumb to help as far as sizing a wastegate based off of the power of the engine. So if you used a 9 horsepower per pound of airflow that the engine would need, you could just take your horsepower, divide by 9, and then that's your mass flow for the turbo. Then we have charts for flow rate for the wastegate. And general rule is that most well-sized turbochargers are going to end up with about 50 to 60% of the total mass flow passing through the wastegate at some point.
Okay. So that's the percentage of wastegating. So essentially how much exhaust gas is being bypassed around the turbine wheel through the wastegate.
Yes. And that would be the easiest general rule to try to figure out how to size something. There's a lot of factors that will,
So sufficiently for a quick and dirty back of the napkin calculation to get you in the ballpark.
Mm-hmm. Yes. Yep.
Now, I'm guessing as well, most enthusiasts probably aren't diving too deep. Obviously, the quick calculation you just gave is simple, but a lot of people probably don't want to do even any math. So I'm guessing though, for common combinations, Evo with XYZ turbocharger or Subaru STI with XYZ turbocharger pump gas, this is our power aim. Someone could ring TiAL Sport or one of your sub dealers and say what size wastegate suits. You got enough data points that you can say, yep, this one will work for you.
Yeah, yes, I would say that's accurate. We've been doing it long enough and have enough points to look at as far as what worked on what cars under certain horsepower conditions and so forth for various, like you said, an Evo build, lots of those, right? Lots of what we select for that. So we would be able to do that. Any of our users or us directly, reach out to tech and we would easily be able to answer, a general question like that.
As I see it, for like mainstream run-of-the-mill builds that have been done 1,000 times, there really should be no sort of issues choosing an appropriately sized wastegate. It's really when you start getting to more bespoke applications, one-off applications where there's a little bit more going on. Now, I talked about the potential downsides of a wastegate that's sized too small. The flip side of that, what are the downsides if you just go and put on the biggest, dirtiest wastegate you can find on a small capacity engine that really doesn't need such a big wastegate?
A little bit of resolution when it comes to, in other words, a very small motion of let's say a 60 millimeter wastegate, for instance, on a 2-liter engine. Generally, most applications, that would be really a large wastegate because your flow rate and a very small change in valve position would create a lot of bypass. And therefore, you might have difficulty controlling it precisely. It can be more difficult to control. Also, the back pressure is again influencing the valve, so you have a limitation in how high you can turn the boost up because you have more and more surface area to work against. And the higher that the boost pressure you run, regardless of the turbo, the higher boost you run, the more force, more exhaust gas pressure, and it's trying to push that valve open under a traditional poppet style wastegate.
Yeah, I mean, I think most people kind of ignore the aspect of exhaust back pressure. We've talked about it dozens of times so far on the podcast, but essentially we've got boost pressure acting on the top of the wastegate on the diaphragm to try and keep it closed if we want more boost, but we are fighting against the back pressure, that exhaust manifold back pressure that's also trying to force that valve open. And as that back pressure climbs at some point, no matter what you're doing, essentially the valve's just forced open by back pressure, correct?
It's going to, at some point, going to be high enough that it's going to push it up, and you can't make any more boost no matter what you put on the duty cycle. It's just it's going to push it open because that pressure is greater than any force you're putting on the diaphragm. That's the way it opens the valve, and you'll see as RPM climbs, the boost falls off. Now the turbo may be out of air also, but generally speaking, it's probably not 100% out of air. You're having to fall off because of that back pressure pushing the valve out.
Yeah. All right. So we're going to end up with a valve that's too big for the application. We're going to end up essentially losing resolution with our boost control. So it will be more difficult to gain stable, accurate boost control and also gain small increments of our boost control where we want it. And also we're going to run into this problem where the bigger the valve, the more likely we are to essentially limit our ultimate boost pressure. Is that kind of a succinct way of summing it up?
Yes. And that's you have to get larger and larger diaphragms to keep that in perspective, right? So you could overpower the valve traditionally if you size the diaphragm proportionally.
Which sort of comes back to what we were talking about earlier. But then also with modern engine bays, we then run into packaging problems if you want to run a large diaphragm.
Yes.
Yeah, okay. Now, another part of the wastegate puzzle that sort of falls a little bit outside of just the wastegate itself is the physical mounting and how it is taken off the exhaust manifold. Can you give us a bit of a rundown on do's and don'ts in that regard?
One of the things we want to try to put a tube on that is less than perpendicular to the exhaust gas flow. So not turning 90 degrees into the wastegate pipe. Also maximizing the size of the feed tube that you're going to use to get to the wastegate. So it's okay to use even if the flange at the wastegate is say slightly smaller, to use a larger tube to get there. So you can prioritize flow. A lot of times there's a compromise. There's compromise from installation, but the bigger you can make it, the better. That means the losses just getting to the wastegate have been minimized. And you don't want to put a bunch of turns and anything that would restrict flow. And anytime you turn it 90 degrees sharp, it's not going to flow well. You're going to automatically reduce your total flow rate capability by going 90 degrees. So you have to size bigger, right? So a larger wastegate, then it means you have to have a larger tube, which will allow more flow. So you end up oversizing the wastegate due to the installation. Sometimes you don't have a choice. I can only put it on at 90 degrees. Then you go, okay, so go to a bigger wastegate then in that circumstance to make sure you get flow getting into the wastegate.
Yeah, there's always sort of compromise in this, and packaging constraints are such a driving force in how we do it. But yeah, I mean, essentially best practice standards here. We want to make it easy for the exhaust gas to flow into the wastegate. So if it has to turn through 90 degrees or, worst case scenario, I've seen 180 degree requirements, it's not going to do a great job of that. And, we jump on the dyno, you do your first pull on wastegate spring pressure and you sort of get to 4,500 RPM and the boost just starts to spiral out of control and you're dead in the water. There's no coming back from that. I mean, I would also say, yes, to a point, oversizing the wastegate in slightly less than ideal installations will be effective. But, when you get to these worst case scenarios, and I've had a few of these on the dyno over the years, you could literally unbolt the wastegate and throw it in the bin, and boost will still spiral out of control. The exhaust gas cannot flow out. So, these are the things that I think they're very important to consider at the outset of a project, because it's very difficult and expensive to find that that's a problem and then have to go back and re-engineer your entire turbo installation. Granted, these days, the quality off-the-shelf turbo kits from high-end manufacturers, this has all kind of been ironed out, and you can probably pretty much guarantee it's not going to be an issue. But if you're doing something one-off, then these are the things you need to consider. Now, the next aspect with wastegates is spring selection. So I'm interested in your take on this. Obviously, we need a spring in the wastegate. Wastegate manufacturers like yourself will give you a spring that has a PSI rating, and say you want 10 PSI, well, obviously it would make sense to choose a 10 PSI spring. That's not always going to necessarily give you 10 PSI in the inlet manifold, though, is it?
For multiple reasons. We'll start with the exhaust side first, which is you don't know exactly what exhaust back pressure unless you measure it from the turbo you have. And it's not always known what that's going to be. And most people have no idea what their exhaust back pressure is. So they don't put a sensor in to measure it. It's not easy to do. So they don't do it. And that will affect it a lot. AR of the turbine, obviously, again, affects it also. On the other side, how much of a pressure drop are you getting through your compressor side? So in other words, sometimes these are quite egregious. Like we've seen customers, when we got them to measure it, see 10 or 15 PSI pressure drop from the turbo to the intake manifold because the piping restrictions, intercooler selection, and you go, this isn't normal. You might want to check what your pressure drop is. And people are often shocked at how much pressure drop they have from the turbo to the manifold.
Yeah, 10 to 15 PSI is pretty out the gate. But and even in a quality intercooler that's sized appropriately for the application, it's not uncommon to see 1 to 2 PSI pressure drop across the core. So
easily, yeah.
What you're seeing in the inlet manifold definitely doesn't represent what the turbo is seeing at the compressor outlet, and at least as far as the turbo is concerned, that's the important part for the turbo.
Yeah. So that's why when you put a 10 PSI spring in there, there's two factors that you don't know, what is the back pressure and what is the pressure loss on the intake side. And those can be both quite egregious in terms of like what they are. And you don't know what they are for every combination of turbo, max. I mean, there's a lot of factors, right? So you try to basically, you go, if everything's ideal, then you're going to get 10 PSI, but you could be plus or minus in probably a lot of circumstances, plus or minus 2 PSI wouldn't be uncommon.
So it's a guide rather than a rule. So essentially, you might have to run the car with a 10 PSI spring, see what you're actually getting, and then adjust the base spring to suit.
Yeah.
Okay. So when we are choosing a spring, obviously now we know that we might not get exactly what we want, but let's say, within reason we are. Let's say we've got a car where we want to be able to run 20 PSI. Is there a downside in using a 10 PSI spring and then electronic or pneumatic boost control to get us to our target? Or, should the customer be choosing that 20 PSI spring, and then are the downsides associated with that? I'm interested in your take on this.
I mean, generally speaking, we would always recommend that you first try to evaluate what's the lowest boost you really potentially need to run, and go. In this case, we'll just assume that as your example is the customer says, I do want to get down to 10 PSI, and he has a reason for that, bad fuel. And so, but I do want to have good fuel. I want to run 20. The problem there is still going to be, again, do you have enough mechanical leverage to control the wastegate to close the valve under higher and higher back pressures and potential intake pressure? So generally we just you want to make it as close to the minimum that you want to run. That would be the recommendation. Trying to go 2 to 1 isn't always going to work. There are many circumstances that it doesn't. I know a lot of people have said, hey, 2 to 1 rate, you should be able to double what your base pressure is. No, I would maybe.
Yeah. There's not a lot of black and white in the world of turbocharging, unfortunately, just a whole bunch of shades of gray.
Because I have to know a lot more to tell you that, you could probably double that, right? And again, it's all devils in the details. You need to know all the details, right, to have a confidence that you can go, oh, yeah, it's going to be able to get double. If you can't get double, that means you have probably some other things you might want to address in your overall turbo system If you can't double it means you probably have like really high back pressure for some reason, or you have an intake restriction or something to that effect. Because as a general rule, it's been, you should generally be able to get 2-to-1 because there's enough leverage. There's about most wastegates have about a 2.5 to 3-to-1 ratio of diaphragm to valve area is a general rule.
So you've got quite a bit of power on that diaphragm.
Yeah, quite a bit of power to do that. And if you're not able to get at least 2-to-1 out of a 3-to-1 ratio, it means you got something that's probably a lot higher than you desire it to be. But, sometimes that's it.
I mean, that's really where gathering as much data as you can, you quickly start to see why these things are happening. One of the things that I actually noticed, and I mean, I've been dealing with turbocharged engines for 20 plus years, 25 years. So I feel like I probably know them better than the average person. Our own race car, which I won't bore you with the details, but essentially a SR20 VE turbo engine with a Garrett GTX 3071. We're running that because it makes a lot of power at even modest boost pressures. We're running that with a relatively soft spring. And I think that got us down to around 10 PSI minimum boost, still making probably more power than we needed. Interestingly, we actually tried swapping that to a 1-bar spring, so 15 PSI spring, and it did what it said on the box. We kind of gained another 5 PSI, give or take. But what I hadn't actually encountered for, I think just that extra spring pressure, not fighting against the exhaust manifold back pressure so much, we actually ended up bringing the turbocharger on about 300 RPM earlier, which for a race application that's night and day. That was a massive gain that I hadn't necessarily expected. Now, yes, you can manipulate this to a degree with electronic boost control, but physically, if you've got a very soft spring, that exhaust manifold back pressure can simply overcome the valve and start opening it prematurely. Is that something you sort of see frequently?
Yeah, so that would be true if you're just running spring only pressures for sure. If you're running, we'll say the older style, needle ball spring design, just manual boost controller, then that would actually be true again also in what you just stated. I think most electronic boost controllers, not all, but today could basically keep it closed during that initial spool up, and so that you really wouldn't see the boost change or the spool up rate based on the fact you can hold the thing closed the whole time.
Yeah, typically most sort of ECUs will have a facility where they'll supply all of the boost pressure to the top of the diaphragm to try and hold it closed until you get to X percentage of your actual boost target. So that should overcome that scenario that I just explained.
Yes, that's true. I would say, like I said, you're going to see what you experience, I think, and if I understood what you said, basically when you gain of 300 RPM earlier boost onset. Yeah, because the valves stay closed longer.
Yeah.
And you gain more, obviously, exhaust gas energy from keeping it closed, and it spooled faster. But again, you probably could have seen the same on the 10 PSI, just as you described. You would just put all the air on the top, and it's going to hold it closed and get a similar response.
Okay. All right. So, I mean, with these products, these have been around, forever. There's not a lot new. Obviously, we've already talked about the materials problems that you saw at the start of it, but I kind of see this market now as being very mature. There's a number of top players in the market producing quality items that just work as expected. Where do you sort of see potential for further iterative improvements with blowoff valve and wastegate technology? Is there more to come?
I would say generally, I mean, there could be a little bit through electronic control systems, right? So if you're electronically controlling the devices, there are nuances that you could improve performance. Electronic boost control is obviously going to provide a more repeatable and stable boost control versus pneumatics. You have all the issues to deal with on installation. If you have a direct electric actuator with direct feedback, you can do a much better job of boost control. You can predict it based off, if you can map it. Right. And then you can't really it's harder to do with a pneumatic, and it's harder because installations vary dramatically. How long is the line between the solenoid and the wastegate? How big is the volume in the canister of the wastegate? There's all these things that are factors. So ultimately, for more accurate boost control, if you can afford full electronic boost control, then it's going to have a slight advantage over pneumatic design.
Seeing as you mentioned that, I think the elephant in the room here is, at least from my perspective, if I look at this industry, you've got TiAL Sport and TurboSmart as probably the two main players there. So, I mean, it's only fair, I think, to compare the two. And obviously, it's no surprise, no new information that TurboSmart have brought out their electronic wastegate. Been out for a little while. On top of that, they've also got their straight gate, which is, I sort of see it, I haven't had the opportunity to play with one, but is on face value something that probably makes a lot of sense. It's one of those like, well, why hasn't anyone else done that kind of things? Is that a direction you want to go in? I mean, I'm not sort of saying necessarily copying the competition. I mean, TurboSmart also didn't create the electronic wastegate. They're the standard in OEs now. So, it's a natural progression. Is that something you want to go down the path of as well?
So from electronic control cost today versus for wastegate control is, you'll get lower costs going forward, and more customers can use it. So we'll most likely be offering an electronic wastegate soon, but it's not, again, it's trying to make it where it's cost effective and can the consumer generally use it.
I mean, I think a good sort of argument for this is my personal take on these. I've seen the technology, and I'm an absolute tech nerd, so I tend to jump on things pretty quickly when they first come out. For our own endurance race car, we run a pneumatic wastegate, and at this point, I really don't see that the juice is worth the squeeze in changing that car over to run an electronic wastegate. I mean, it's one of those cases where if it isn't broken, don't fix it. It works exceptionally well. I understand the technology. I've got exceptionally good boost control. Normally, I'm chasing my boost target to within plus or minus maybe 0.2 or 3 kPa, which I consider to be pretty damn good. So there's not really enough driving me to kind of make a change and then learn a whole new technology and then overcome the obstacles that I'm probably going to find. And I think probably a fair few people would be in my situation as well.
I think it's a fair analysis of, is there enough gain for electronic control? I think there are circumstances where, yes, it's worth it, right? But I would say in most applications, pneumatic is doing a very good job and generally is satisfactory for most. And again, there are always exceptions to that, clearly,
Yeah. All right, let's sort of also talk about your relationship with Robert Young from Force Performance, past guest. So we've sort of talked about Xona Rota and also how Robert has been working with TiAL Sport for the Force Performance product range. Obviously we've talked about Xona Rota with Robert, so I don't want to do a super deep dive on that again, but just to sort of get an understanding of that. So what is the connection that you have with Robert Young, and how did that sort of start?
Our relationship started in the mid-'90s when he started his company. Actually, we knew each other a little bit before he started his company, Force Performance, and then basically he was a customer. And we were manufacturing. I mean, he didn't necessarily have manufacturing, but he was a turbocharger builder, right? So he had, simple turbochargers. Had desires to have some other products that would be unique to Force Performance. So we worked together to help. We did design and manufacturing for his request, right? Like he's like, I need this thing. You guys can make that for me? I'm like, sure, we can make those things. So
on that note, is that a service that TiAL Sport offer to others, or is that unique with the relationship that you had with Robert Young? I can imagine if you're sort of doing design and machining work for dozens or hundreds of different people, you kind of like spread yourself very thin and take your focus away from TiAL Sport itself.
I mean, we look at it as that relationship is kind of additive to the business we're doing. Because it's in the same market, we're utilizing the same equipment, so forth. So it's kind of an add to business. It's not like somebody's coming to ask us to make something that we're not familiar with. So it's easier. We understand the product, so like we can provide engineering services that are valuable from a standpoint of design. A customer has a desire. I mean, we work with many customers, and we've designed many products that are turbocharger related products for customers because it facilitates a broader business scope for us to do more turbocharger sales, more wastegate sales, by helping a customer be able to sell more products. So we haven't done it exclusively for FP. We did a lot early on with FP. The relationship worked well. He had things that he wanted to have for his market, and we're like, yeah, sure, we can do those things. So that we do it for other companies too.
All right. So at what point did it make sense to join forces on the Xona Rota project?
I think it evolved over multiple years. We were doing early days. We were modifying, Garrett turbochargers and making billet compressor wheels for the turbos, right? And that just continued to evolve. And there was always, as you're trying to go faster and make things go better, more power. It's like, okay, so where are the limitations? And ultimately, we decided it was, it evolved to the point where we wanted to build our own turbocharger because of the at the time limitations within the current offering. And so that's when we decided we would go and combine to do this on a rotor turbo.
Okay. On that note, so can you kind of give us a bit of an understanding of how you and Robert work together? So what your individual roles are within Xona Rota as a business?
At the start, we were, TiAL being an engineering company where we have probably a staff of 5 or 6 full-time engineers to be able to do design work. So we did all the design work effort behind it, and Robert would do the assembly.
Yeah, okay. That makes sense. In terms of the challenges involved, I mean, obviously you've been deep in the turbocharger and turbo system market anyway, but what are the challenges you sort of found when it came to actually manufacturing a complete turbocharger from scratch as opposed to, a billet compressor wheel or maybe a turbine housing?
Challenges would be, what are we going to improve? Like, what are we done? I think kind of the basis of the turbo, or the evolution of the turbo that we've decided to bring to market versus what we had been utilizing, was what can we do to do a better job? Like, what are the things that we see as weaknesses in those particular products, and then work towards that. So the challenge obviously is one of them is obviously the bearing system, and having ball bearing system that works, right? We knew we wanted a ball bearing system in the turbo because of durability. And what else could we do to improve that? And of course, we developed a patented system that we have, and we have a patent on it for a hydraulically preloaded bearing system. There's lots of advantages that I won't dive deeply into what those advantages are, but
yeah, we did that with Robert. So if people haven't listened to that episode, this would be a great time to go and get a full understanding of that bearing system, because it is quite unique.
So that was, one of the bigger challenges, like understanding what tolerances that you would need to do. It's very technical, right? And the tolerances are very challenging to hold to get a ball bearing turbocharger to be reliable. And it's primarily related to obviously the bearings themselves. And that was kind of where that was the most challenging. All the other items we'd already kind of done already, right? So those things were already known, like, for the compressor wheel, design turbo housings. We knew how to do that already. So those things were something we'd already accomplished.
So it kind of really, seems like an obvious step, really. You kind of got all of the other supporting products. Let's just make this one, albeit very complex, part of the puzzle. And then you're kind of standalone and then not beholden to other manufacturers on supplying the parts, which is a big issue that Robert pointed out as well.
There was often a supply issue, getting product in a timely fashion. And that was another reason. And we just wanted to offer features that just were never really offered in a turbo, right? So what can we do that we would hope that people will find interesting and useful features? So obviously more and more design. How do you get better? How do you continue to evolve your product? And that's kind of where we are today in terms of,
It's interesting that you raise that, because this is my next question. I've been, as I mentioned, in turbocharging, or dealing with turbocharged engines and tuning them for a couple of decades or more. Particularly over the last, I'd call it 10 years, although maybe it's a bit longer than that. I've just seen this sort of hockey stick exponential improvement in the turbochargers that are coming out in this performance aftermarket. And what that means for the enthusiasts is we're getting turbochargers that are kind of giving us the best of both worlds. We've got low boost thresholds, great boost response, minimal lag, but the power levels that we're getting out of these turbochargers are just through the roof. It's great. I'm here for it. My question is twofold. One, what has brought about this exponential improvement in turbo performance? And two, can we expect a similar trajectory in terms of the next 5 years, or are we going to start tapering off and seeing smaller and smaller iterative improvements?
I think that, more recently, so we've done, Xona Rota has had a couple steps, I'm sure. And one was in offering the turbine wheel. We offered that in 2019, and that provided a significant improvement in overall performance for our turbocharger. And then recently we have just introduced the new compressor era. So after significant, we've spent thousands of hours of CFD time. And what it is that it's trying to figure out where has somebody not gone with the product, right? So how can we have a much better product today than say anybody else who's making turbochargers for the market? And that's the key to getting to a higher performance level. And is there an end to that? It just depends on how much money you want to spend in development, I suppose. It really is a dollar limited. We still see that there's significant improvement yet to be made from a performance standpoint.
I mean, it's definitely exciting times for any enthusiast in the turbo world, because we do have access to products that are just amazing. I kind of wish I could go back now and have access to the current crop of turbos. Back when I was drag racing my Evo, we were stuck with a dirty old HKS T51R SPL ball bearing turbo, which, by today's standards, let's be honest, it's a bit prehistoric. It got the job done, but we're seeing, significant boost hitting at about 7,000 RPM, kind of just about the point that a stock 4G63 is hitting the rev limiter. That was fine for us because we're revving it to 10,500 RPM. And of course, the requirements for a drag car are very different to a street car. I think the street car market is probably harder to size a turbocharger for or make quality turbos because, the power is probably less important, I think, than the response and the boost threshold. Would you tend to agree with that?
Yeah, I think yes. What we've been able to do with the significant amount of R&D time is to figure out how can you get an even wider operating map for the compressor. And that's the key to get everything is, can you make a wider, more efficient power band for the turbos? And that's what we've seen with the most recent developments. And I think that there's still, I know that there is, not that I'm going to say specifically what area we're going to go into to get better performance, but that we already know, we've already experimented with something that we want to introduce into the market maybe another year or two down the road, but can again offer additional overall performance boost to the turbo. So I still see that there's room to do more for the future for turbo. Yeah.
Exciting times. I mean, no doubt there will, but it just still blows my mind how quickly things are proceeding. But as I say, I'm absolutely here for it. Look, Greg, I think we'll move towards wrapping this thing up. And of course, we've got the same three questions we ask all of our guests. And the first of those is, what's next in the future for you, for TiAL Sport and Xona Rota? You got a bit going on here.
Well, I mean, a lot of our time today is primarily turbochargers, where we spend most of our R&D time today. Like I said, we have a wastegate for TiAL, but for Xona, where most of our engineering efforts go to designing new turbo housing, new applications. So it's going to be just more turbocharger, either from a performance standpoint, more applications, and actually expanding the lineup of turbo. We're going to have larger frame turbos, more prevalent coming later half of this year and then into 25. So that's where we see our growth.
Sure. To me, from the outside looking in, that makes perfect sense. As I already mentioned, I sort of kind of see that too. The blowoff valve and wastegate market is pretty mature at this stage. And as we've just discussed, obviously there's still potential for improvement in the turbocharger market. So it's a sensible place to be focusing your energy. Next question, is there any advice you give to a younger version of yourself to help reach where you are today in your career faster?
Yeah, it's such a different market today. And there's a lot more competition in that arena. It's just a completely different environment today. And I don't like to discourage people from chasing their dream. I think if you're a strong-willed individual and you're determined, you can do it, but you better really have a passion to do it, because otherwise you probably would result in not finishing the job. So it's I think what we see in the marketplace, with Asian manufacturing and so forth, is it's very difficult to invest and spend money in the market when that's going to be not very long lived, right? You're going to have a copying that happens, right? So it's that is a problem. Try to be positive on these things, but it's an extra hurdle that you have to consider when you're trying to invest in a business to create, be making turbo or a wastegate or a blow-up valve. Is who's your competition?
I mean, it's always difficult coming into any established market with some big players and trying to compete on an even footing. So yeah, I mean, granted, that is going to be difficult. It's going to also demand substantial financial resources. I think I'll focus on the one point you made there, though, that I think goes across the board for all industry and all vocations is do something that you're incredibly passionate about. It's going to make it not a chore to get up in the morning and go to work. And I think that's what separates, I have a job that I absolutely love and have the whole way through. And I think that's really important because you spend so much of your working life doing exactly that, working. I really do pity the people that kind of are stuck in a job because they need the paycheck and absolutely hate their day-to-day life. Why not try and find something that you're genuinely passionate about?
Yeah, that's probably the most sound advice for anybody wanting to start a business, because if it's just going to be work, you probably don't want to own a business.
Fair. All right, we'll finish off here, Greg. The last question, if people want to follow you and see what you're up to, how they best to do so, what are your websites, social media, etc.?
Well, we have TiALsport.com, which would be our website. We have Facebook and Instagram for TiAL Sport, and the same would be true for Xona Rotor.
Perfect. And as always, those links will be in the show notes to make it easy for people to find. Look, Greg, it's been a real pleasure. I mean, obviously, the TiAL Sport name has been in the industry as long as I've been in it. So great to finally actually chat face-to-face or podcast-to-podcast with the founder. So thank you for your time today, and we wish you all the best for the future in your product development.
Thanks for having me on. It's been a good time.
If you enjoyed this episode of Tuned In with Gregg Jones, we'd love it if you could drop a review on your chosen podcasting platform. These reviews really help us to grow our audience, and that in turn helps us to continue to get more high-quality guests. To say thanks, each week we'll be picking a random reviewer and sending them out an HPA t-shirt free of charge anywhere in the world. This is also a great place to ask any questions you might have too, and I'll do my best to answer them if your review gets picked. So this week, a big shout out to Hads from Australia, who has said, while my head and heart have always been with old school Ford four-bangers, overhead valves and Weber carbs, I thoroughly enjoy every episode of the HPA podcast. Whether it's technology being used to create power figures that not so long ago were unthinkable, fabricating and designing to create automotive works of art, or even just simple philosophies or attitudes your guests have used to help them achieve their dreams and goals. Well, it's great to hear that you're seeing value in the podcast and enjoying them, and if you get in touch with your t-shirt size and shipping details, we'll get a fresh tee shipped straight out to you. All right, that concludes our interview. And before we sign off, I just wanted to mention, for anyone who's been perhaps hiding under a rock and hasn't heard of High Performance Academy before, we are an online training school, and we specialize in teaching a range of performance automotive topics, everything from engine tuning and engine building through to wiring, car suspension and wheel alignment, data analysis, and race driver education. Now, remember, you've got that coupon code. You can use podcast75 at the checkout to get $75 off the purchase of your first course. You'll find our full course list at hpacademy.com/courses. Important to mention that when you purchase a course from us, that course is yours for life as well. It never expires. You can rewatch the course as many times as you like, whenever you like. The purchase of a course will also give you 3 months of access to our Gold membership. That gives you access to our private members only forum, which is the perfect place to get answers to your specific questions. You'll also get access to our regular weekly members webinars, which is where we touch on a particular topic in the performance automotive realm. We dive into that topic for about an hour. If you can watch live, you can ask questions and get answers in real time. If the time zones don't work for you, that's fine too. You're going to get access as a Gold member to our previous webinar archive. We've got close to 300 hours of existing content in that archive. It is an absolute goldmine. So remember that coupon code podcast75. Check out our course list at hpacademy.com/courses.